Hi everybody, Patrick here from www.engineeringshock.com and www.electroniclessons.com. I've had some requests lately to start doing some tutorial videos, so I figured why not start with a good old clap detector circuit. So what we're going to do is we're going to build a clap-on, clap-off device, single clap, and we're going to build a circuit that handles the audio signal and toggles a relay. So really you're going to learn quite a bit of theory. We're going to show you some oscilloscope plots, and we're going to start off with the main circuit here. It just requires two resistors, a capacitor, and a condenser microphone or a electret microphone. The first resistor is 10K, second is 100K. The first capacitor is 0.1 microfarads, and the microphone, just a standard microphone. You can get them at Radio Shack, you can get them on eBay. They're relatively easy to find. Sometimes they're polarized, but this one isn't polarized. So what I'll do is I'll draw you the schematic, and I'll tell you how it works. On the schematic, this is our 5-volt source. It can come from a 7805 5-volt regulator, or it can come from a variable power supply circuit, or it can come from a wall wart. I can elaborate more on this in another video, but this is the schematic for your power supply, and this is the positive end of your power supply, and anything denoted by the triangle facing down is your common ground line. So what we've got here is a 10K resistor in series with the positive DC line, and in series with that we've got our condenser microphone. This resistor acts to protect the microphone, as well allow us to couple a signal across the microphone when it makes a detection. Think of the microphone almost as a little transistor. When it detects noise, we'll get a little vibration along this line. So when the microphone detects audio, what'll happen is on this we'll get that little tiny signal across this coupling capacitor, the 0.1 microfarad coupling capacitor. So if we measure here, between here and ground on our multimeter, while we're blowing into the microphone, we might see a millivolt or two on our digital multimeter, but we won't see much. Now if you have an oscilloscope and you probe right here and you start talking to the microphone, and you bring the voltage per division scale up, you'll be able to see something. And I'll show you that in a minute, because I'm going to construct this, and then we're going to go on to see how we can make that signal bigger and make it usable. And we can change sensitivity. So first of all, I'll build this circuit up. I will probe this on my oscilloscope, and I will show you what that signal looks like. So as you can see, I've got my ground line and my positive DC line. I've got 5 volts on this wire. And so the top rail here, the top rail of my breadboard, will be our positive DC rail, and the second rail from the top will be our ground rail. Anyway, we have our 10K resistor in series with our microphone, and our microphone, the secondary pin on the microphone, is connected back to our ground line via this big wire here. And we've got our coupling capacitor right here along the 10K resistor and the first lead of the microphone, and we've got our 100K pull down resistor here. So when I probe this line on my oscilloscope, I'm going to bring the voltage per division up so we can actually see the signal. Now we're going to have to amplify the signal later on, but first of all I'll just show you what I see on the oscilloscope. Now it might be a little bit hard for you to see, but I've got the time per division set for just a few millivolts per division. So when we clap, or when the audio detects anything, we get a little spike on the line. Now again, what that coupling capacitor does, it acts to rid the circuit of its DC component as well. So all we get is a flat AC tone. But what we need to do in order to use that for a switch, we need to amplify that out to a nice square wave, 5 volts. So next we're going to talk about the amplification stage. Okay, it gets a little bit more complicated here, but bear with me and we'll get through it. What I wanted to do was amplify the output of our audio signal so that we can turn it into a square wave. And we're going to do that in 2 stages. First we're going to amplify it, and then we're going to set it through a comparator circuit. Don't know what I'm talking about? Don't worry, as long as you follow along you should. So what I've got here is what's called an LM324 quad op amp IC. And what that means is it's got 4 operational amplifiers on board. This is the schematic symbol for an operational amplifier, and our circuit is set up for a non-inverting configuration. And I believe that the voltage gain formula is 1 plus RF over RA, RF being the feedback resistor, and RA being the resistor connected between pin 2 and ground. So in this case, I've got a variable resistor. You don't need to use these values specifically. I've got a variable resistor here set to a 100K variable resistor between pin 2 and pin 1, which is the first of 4 op amps. We're going to use 2. So in this case, if this variable resistor is set to 100K, then our voltage gain will be 100K divided by 1K, which is 100 plus 1. So our gain should be 101. So if we have 1 millivolt at pin 3, then the output should amplify by 101 times. So we should have 101 millivolts at the output roughly. That's you're going to have what we'll have here is we should have nothing thanks to this pulled up resistor until we hear some audio here. So this is going to allow you to really customize your circuit with sensitivity, because if you bring this down to say 50K, then your output, your voltage gain is going to be 51. If you bring it down to 20K, 20K divided by 1K plus 1, you're going to have a voltage gain of 21. So multiply that by whatever voltage is at your input, and that's what your output should be. So if we clap and we've got a relatively good voltage gain here, we're going to see a relatively large spike at the output. But that's not what we want. We still want a square wave. We don't want a jumbly, weird looking wave. So what we're going to do is we're going to feed this through another operational amplifier in a different configuration. It's called a comparator configuration, and I'll get to that in just 1 second. Now before I do that, I've labeled each of the pins here. Pin 4 of the LM324 is connected to 5 volts. In this case, we would just call it VCC. That's the power line for the chip. Pin 11 is your ground pin. So pin 4 is on the bottom here. Pin 11 is on the top. You can find the pin out for the LM324 online, but I've tried to label each pin here on the inputs and for VCC and for ground. So here we've got a nice amplification circuit. Now we're going to compare it. So we're going to set through a comparator circuit. I'll show you what that means, and you'll see exactly why it's necessary. We feed the output of the first op amp, pin 1, to the positive input of the second op amp, which is pin 5. What we have here is we have a resistor divider. So since we have 5 volts here, and we've got 2 equal resistors here, both at 10K, we're going to have 2.5 volts here. What I've done here is I've denoted this as VCC, so anywhere where you see this line, VCC, it means that's connected to 5 volts. So anyway, what we've done is we've connected this 2.5 volt voltage division to pin 6, which is the negative input of the second operational amplifier. So what happens here is we've always got 2.5 volts as a reference on the negative input, which means that the output will always be low. When the voltage at the positive input exceeds the voltage at the negative input, we're going to see a nice square wave output, 0 to 5 volts. And this is our processed signal. We've got an amplification stage, and we got a comparator stage. So instead of getting a wonky signal and using that, we're going to use a nice square wave signal. So again, we've always got 2.5 volts at pin 6, the negative input. And as soon as we get a voltage that exceeds 2.5 volts at the positive from the first op amp, we're going to see square waves. So likely, since audio frequency is AC in tones, we're going to see a ton of square waves here. We still can't use that for a switch because we need one solid square wave to turn on a switch. So we've still got some work ahead of us. Now this circuit I want to add is, you can manipulate it, you can modify it as you see fit. You don't need to go all through this, but what I'm going to try to do is I'm trying to give you one of my designs. I'm going to try to give you all that you need to do, or all the information you need to build and modify your own circuits as you need them. So I hope I've been articulate so far in how to build this. You don't need to use an L324. I just prefer to use them because they're very easy to work with. So now what we want to do is we're getting a square wave, but we're going to get a lot of squares, and we only want one square. So what we're going to do is we're going to feed this into a retriggerable monostable multivibrator that'll turn these several square waves each time you clap into one long square wave. And then we're going to feed that into what's called a toggler circuit. We're going to use a JK flip-flop for that. So next I'm going to break out the 74LS123 monostable multivibrator circuit. Before I get to the next stage, you can't really see the chip all that well because it's buried behind all those wires. But here's my variable resistors here. You can barely see it. That's going to adjust sensitivity. I've got the 1K ohm resistor on the first negative input and tied between the first negative input and ground. Sorry, pin 2 of the first op amp. You can't see that either. I've got my resistor divider, the two 10K resistors for the comparator circuit there. So I can right now I've got it set up so that I can adjust the sensitivity, and I've got my oscilloscope probe set up to the to the output of the second op amp, the comparator op amp. So let me just show you what the output looks like. So right now I've got it set to 5 volts per division. Now I can set the sensitivity, as I'll do that right now, on the potentiometer, so it'll even pick me up talking. Hello, 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 hello. But we don't want that. We don't want that at all. We want to make it so that a nice loud clap will activate this. So I'm going to bring the resistance on the variable resistor up, and now it shouldn't pick me up talking, but it should pick up my clapping. So that's the square wave output. Next, as I said, we're going to talk about our monostable multivibrator circuit. Okay, I know this looks a little bit jumbled, but follow along. Right here on this is our 74LS123A, and that is our monostable multivibrator circuit. Let's just put the indicator in here. Yeah. So this is pin 1, pin 2, pin 3, pin 4, pin 5, pin 6, pin 7, 8, 9, 10, 11, 12, 13, 14. Pin 14 is connected to 5 volts, pin 7 is connected to ground. Pin 1 is also connected to ground, and pin 2 is connected to what I've labeled A, and that's the output of our comparator. So that's our square wave input. Make sure you connect it to pin 3. Pin 2. Pin 3 is connected to VCC, so 5 volts, and that's our clear line. Now we could put a power on reset circuit here, but we're not going to worry about that because we're going to use that later on when we use our flip-flop. Now rest assured, we're almost done. But what this circuit again will do is it will turn a bunch of square waves into one long square wave by retriggering a certain delay after every single pulse. So if this pulse keeps occurring, then this long singular pulse will just keep growing in length. And once these pulses stop, this will finally go down. Now the calculation for this is based on two components, an RC component. We've got a 100K resistor and a 10 microfarad capacitor here. The 100K resistor is tied in series to VCC and pin 13. And then right under the resistor we've got the positive side of an electrolytic 10 microfarad capacitor, and the negative side is connected to pin 12. Now here's the calculation for it. This calculation, the delay equals 0.33 multiplied by R multiplied by C. So that's 0.33 times 100K, so 100,000, times 10 microfarads, which is 0.00001. And that gives us a delay of 33.33 seconds per pulse. So this is a retriggerable monostable multivibrator. So for every single pulse that we have, we're going to have a 30.33 second delay. And every single time we get another pulse, it'll just start that delay from scratch. Hence retriggering. We're retriggering it. So when we clap, we get that that tone of square waves here, what we're going to get, what we want to turn it into is one long pulse. And this will become more, this reasoning will become more apparent when we talk about the flip-flop, and that's pretty much the end of our circuit. But what I'll do is I'll probe the output, which is I've labeled B here on the scope, and I'll show you. And I'll actually throw in an LED to show you how our circuit has been conditioned so far. So I'm standing in the back probably about 2 meters away right now. So I'm just going to clap. Now before, we just saw a bunch of square waves. Now we're just going to get one clean single wave. Now if I keep clapping, now I hopefully this is starting to make sense. That was one long pulse based on a lot of noise being detected by the microphone. So that's our delay. Now you get one clean pulse, and we can use that to trigger our toggling circuit, which is going to be comprised of a 74LS 109A, which is a JK flip-flop. Now I know we got a lot of hardware here, but again, you don't need to worry too much about this. You can just use bricks of this, electronic bricks of this design. As long as you understand what each brick is doing, then you can base your own, you can make your own modifications and really make this circuit your own. So anyway, let me show you the circuit. Here is our 74 LS123 TTLIC. We have our capacitor and resistor network made up of the 100K resistor and the 10 microfarad capacitor up in here behind this wire near the oscilloscope probe. You can't really see it. And basically we've just got everything wired up to as seen in the schematic. So I'm just probing the output right now, which I believe is pin 11. And so we're going to feed pin 11 to the input of a toggler configuration, which it's called a flip-flop. We're configuring a JK flip-flop. It's called a JK flip-flop as a toggle circuit. Now, if you're not familiar with flip-flops or any of these, just Google them and you'll get a better understanding. So we're going to set up a 74LS123 chip on the board, and then we'll show you why. Just to give you a visual of what's going on, so that signal will be fed into our flip-flop, which I'll talk about next. This is our flip-flop circuit. It's based on a 74LS109A TTLIC. We've got pin 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And our indicator. Pin 16 is connected to 5 volts. That's the power supply for this chip. Pin 8 is connected to ground. That's our DC ground for the chip. And now we've got a bunch of inputs and our output. Our output is here, which is pin 6. But a JK flip-flop, essentially how it works is it's got many different configurations. But what we want to do is set it up so that every time a pulse hits the CP input, which is pin number 4, the output will toggle from either high to low or low to high, depending on what last logic state it was in. So what we've got is pin 1 is our clear input, and we've got what's called a power on reset circuit here. So what we've got is a capacitor, a 10 microfarad capacitor, and a 10K ohm resistor tied to the VCC line. So what happens is that 10K resistor limits current to this 10 microfarad capacitor, which means it slowly charges up to a point where it slowly charges up to 5 volts. So when you power it on, the output starts in a 0 state, because sometimes when you power it on, if you just have this tied high or low, your output might end up starting high or low. We always want it to start out low, always. So we got this. So as this capacitor, the voltage on the capacitor slowly charges, eventually the chip becomes enabled. So it starts off in a clear, and then after a few milliseconds, based on the values used for your RC power on reset circuit, the chip will become enabled. So we're just making sure that it doesn't start off in a known state, or in an unknown state rather. Anyway, getting past that, we've got 5 volts connected to pin 2, which is our J input, and VCC connected to our set input. Now I suggest really learning a bit more about the JK flip-flop. There's many different kinds of JK flip-flops, but so standardly, if you connect the clear input, the set input, J and K input high, then you're set to toggle mode. However, in this case, the K input, which is pin 3, is active low, or rather has an inverted it's an inverted input. So we want to tie that to ground, because the chip actually sees that as a high because it's an inversion. So we've got J connected to 1 on pin 2, K connected to ground, which is pin 3, and set pin 5 connected to 5 volts as well. Our clear input will eventually be tied high based on the power and reset circuit once the capacitor charges through the current limiting resistor. And then what we've got is B connected to our CP input. Now that's our clock input. So on the first positive rising edge of the waveform coming in from the monostable multivibrator, the output will toggle. So the output here, if you put an LED on it, which is actually what we're going to do, just as an example, will toggle from low to high, and then I clap again, and it'll go from high to low. So I'll show you what I mean here because I've got the circuit set up. Now this is actually the end of the circuit. Now we can tie a relay to this if we want to. We can do a whole ton of stuff. I'll show you how to tie a relay to it, but really if you're just looking to turn an LED on and off based on clapping, you've done it. This is it. So let me show you the LED. I'm powering it on. And that's me powering it off. So that's that. If you want to toggle an LED, we've fully processed the signal from from scratch, from just an audio signal. We've amplified it. We've made it into a square with a comparator circuit. From there, we made the tone we got from the comparator circuit and turned it into one long pulse, and we sent that one long pulse into our toggle circuit using the flip-flop. Now, if we hadn't used the monostable multivibrator, we would basically be toggling this on and off hundreds of times, because when you, even that one clap, keep in mind the circuit's off right now, it would send hundreds of square wave pulses into the flip-flop, which would turn it on and off hundreds of times. You know what I mean? So that monostable circuit is very necessary. You can use a 555 timer setup in monostable mode, but now we're almost done. At this point, you really should have a lot of tools to work with if you want to build or modify your own. But let's add a relay so you can control AC devices. In the case of wanting to control AC devices using your little circuit, what we're going to do here is we're going to create a little relay driver circuit. So here's the output of our toggling output of our 74LS109NA JK flip-flop toggling configuration. We've got a 10K protective resistor on the base of a 2N2222 NPN transistor. The emitter of the transistor is connected to ground, and the collector is connected to one of the relay coil pins. The secondary relay coil pin is connected to 5 volts. We've got a protective diode here to protect the circuit from when the relay is turned off, the magnetic field on the coil collapses, and this diode protects the rest of your circuit from over voltages. It shunts voltages at the high frequency spikes, because when the magnetic field collapses, you get a nice big spike. Anyway, you need that diode. You need to place the anode to the collector of the transistor, and you need to connect the cathode, which is the negative, to your VCC line. Anyway, I'll get back to that in a minute. When power is applied through the base of the NPN transistor, when the output of the flip-flop is high, the relay transistor turns on. So power sinks through the relay coil, creating a magnetic field through the transistor into ground, completing the circuit. So then our coil is magnetized. Now, for those of you who don't know much about relays, what it is you can control high-power devices using a switch that's created by this little magnetic field. there's three terminals in the inside of a standard relay. There's the common pin, CO, the NC pin, which is normally connected to common pin, and the normally open pin, which is normally open and not connected to common. So when the relay is activated, what happens is the common pin is no longer connected to the normally connected pin. It shifts over to connected to normally open. So then you can control AC devices. What you can do is you can connect the hot wire of an AC device to the common pin, sever it, and connect the other side of that hot wire to your normally open pin. So when the relay is activated, your hot wire is reconnected to your AC device from the common pin to the normally open pin. That's how I do it anyway. I've got a lot of other videos. We've got a relay kit in the store, so check us out if you can at engineeringshock.com. But that's an option. I'm going to show you how to do it. I'll throw it on the board just to give you an example. You need a 5-volt relay because, again, we've only got 5 volts. 5-volt relays are very cheap. They can be found on eBay really easily, and for really cheap. In fact, all these parts can. Look on eBay. eBay's great. So I'll hook it up, and then I'll close off the video. This is the 10K resistor coming from the output of our flip-flop, going to the base of the 2N2222. Which is the middle pin. The rightmost pin is the collector and is connected to one of the coil pins of the relay, and the emitter of the transistor, which is the leftmost pin, is connected to ground. Up here we've got 5 volts connected to the other side of the coil, and we've got our diode in place. Now this relay, it wasn't meant for a breadboard, so I wasn't able to connect any AC up, but I've got other videos that show me using the similar setup that you can actually show. You'll actually see me using controlling an AC device using digital signals. But anyway, since if I clap, you won't be able to see any kind of reaction, but you might be able to hear one. If I'm very quiet and I blow on the microphone, you might be able to hear the click of the relay. So let's just give it a chance. Now, I'm sure you heard that. That was me toggling it on and off. Now, if you blow on a microphone, it's like blowing on any microphone. It creates, it really does create a lot of amplitude at the output of our circuit. Now, from me talking here, I've got the sensitivity set so that I won't set off the circuit, and normal talking won't. But if you blow into the microphone, you certainly will. Now, this is a lot of circuitry. If you have the chance, I'm going to turn this off. If you have the chance, what you can do is, if you know, get into microcontrollers, you can cut out most of this circuitry. I've got a few instructables that show much simpler ways of going about this, but this really gives you a lot of tools. I'm hoping you like this. Please, if you enjoyed this tutorial, let me know, because I'll continue making them. Otherwise, you know, they're very time consuming, so I don't know if I'll continue doing them. I need some feedback from the viewer. I know they can be a bit complicated, but try to bear with me because I'm trying to give you as much knowledge as I can. Anyhow, I hope you've enjoyed it. Thanks for watching.